Welcome back to another Sleepy Steve story. Before we drift off tonight, remember to subscribe to help Steve-O out, and I will keep making more sleepy stories to help you study gently, revise quietly, and settle your mind at the end of the day. Tonight, we are moving into Unit 3 Chemistry, Area of Study 2. In the last few episodes, we spent time with fuels, combustion, calorimetry, galvanic cells, and fuel cells. We thought about how chemical reactions can release energy, how energy can be measured, and how redox reactions can be used to produce electricity. Now we are going to turn quietly toward the question of speed. Not speed in a race, not speed on a road, but the speed of chemical reactions. Tonight's episode is about reaction rates and collision theory. You might picture a calm chemistry laboratory at the end of the day. The windows are darkening. The room is still. On one bench, a small beaker of clear acid sits beside a piece of magnesium ribbon. On another bench, a stop clock rests quietly, waiting to measure time. There is a conical flask nearby, a measuring cylinder, a thermometer, a watch glass, and a small container of powdered calcium carbonate. Nothing is dramatic, nothing is rushed, but every object in the room is part of the same simple question. How fast does a reaction happen, and what can change that speed? In chemistry, the rate of reaction describes how quickly reactants are used up, or how quickly products are formed. If a reaction is fast, the concentration of reactants falls quickly, or the amount of product rises quickly. If a reaction is slow, the change happens more gradually. A match burning is fast. Rust forming on iron is slow. A tablet fizzing in water is faster than a rock weathering in the rain. A fuel exploding in an engine is faster than food slowly decomposing in compost. These are all chemical changes, but they do not all occur at the same rate. So tonight, we are going to slow down the idea of reaction rate and look at the particles inside the reaction. Because at the particle level, a chemical reaction depends on collisions. Collision theory says that for a reaction to occur, reacting particles must collide with each other. But not every collision leads to a reaction. This is one of the important ideas. Particles may bump into each other and simply bounce away. For a successful reaction, particles must collide with enough energy and in the correct orientation. Enough energy means that the particles must overcome the activation energy of the reaction. Correct orientation means that the reacting parts of the particles must be lined up in a way that allows bonds to break and new bonds to form. So we can imagine the particles in the beaker moving, turning, drifting, and colliding. Some collisions are too soft. Some collisions are at the wrong angle. But some collisions have enough energy and the right orientation, and those collisions are successful. Those are the collisions that form products. This is the calm heart of collision theory. For reaction rate to increase, there must be more frequent successful collisions, or a greater proportion of collisions must be successful. In a VCE chemistry answer, this link is very important. It is not enough to say that particles move faster. The stronger answer says that particles move faster, so they collide more frequently, and a greater proportion of collisions have energy equal to or greater than the activation energy, increasing the number of successful collisions per unit time. That is the kind of linking language that turns a definition into an explanation. Now let's return to the quiet bench. Imagine the beaker contains hydrochloric acid and a small strip of magnesium is placed into it. Tiny bubbles begin to appear. Hydrogen gas forms. The magnesium slowly disappears. If we wanted to measure the reaction rate, we could measure how quickly the magnesium is used up or how quickly hydrogen gas is produced. We might collect the gas in a gas syringe and record the volume every 10 seconds. Or we might measure the mass of the flask and contents, watching the mass decrease as gas escapes. Or in another reaction, we might measure how long it takes for a cloudy precipitate to obscure a cross beneath a flask. Different reactions can be monitored in different ways, but the principle is the same. Reaction rate is about change over time. A rate can be calculated by dividing the change in amount, concentration, mass, volume, or another measurable variable by the change in time. A steeper graph usually means a faster rate. A flatter graph means a slower rate. At the beginning of a reaction, the rate is often fastest because the concentration of reactant particles is highest. There are many particles available to collide. As the reaction continues, reactants are used up. There are fewer reactant particles. Collisions become less frequent. The rate slows. Eventually, the graph may level off because the reaction has finished, or because a limiting reactant has been used up. So when you see a reaction rate graph, imagine the particles underneath it. At the start, the beaker is busy. Particles are close together. Collisions are frequent. Then, slowly, the busy movement becomes quieter. There are fewer reactant particles left. The rate falls. The graph settles. Now let's think about the first factor that can affect reaction rate: concentration. For reactions involving solutions, increasing the concentration of a reactant usually increases the rate of reaction. A more concentrated solution has more reactant particles in a given volume. This means the particles are closer together. They collide more frequently. If more collisions occur per unit time, then more successful collisions can occur per unit time, provided the collisions have enough energy and the correct orientation. So, if magnesium reacts with a more concentrated hydrochloric acid solution, the reaction will usually occur faster. More hydrogen gas may be produced in a shorter time. The magnesium may disappear more quickly. The graph may have a steeper initial slope. The important phrase is collisions per unit time. A higher concentration increases the frequency of collisions per unit time. That increases the rate. Now let's think about pressure. Pressure affects reactions involving gases. When the pressure of a gas mixture increases, the gas particles are forced into a smaller volume. They are closer together. They collide more frequently. So for gaseous reactions, increasing pressure can increase reaction rate because the frequency of successful collisions per unit time increases. This is very similar to the concentration explanation, but it applies to gases. In an industrial process, controlling pressure can be important because gases are often reactants. A higher pressure can increase reaction rate, but it may also require stronger equipment, more energy, and higher costs. This becomes important later when we think about optimizing chemical processes. Chemistry is rarely just one idea by itself. Rate, energy, yield, cost, safety, and sustainability are often linked. Now let's move to temperature. Temperature has a strong effect on reaction rate. When temperature increases, particles have more kinetic energy. They move faster. Because they move faster, they collide more often. But even more importantly, a greater proportion of particles now have energy equal to or greater than the activation energy. This means a greater proportion of collisions are successful. So increasing temperature increases reaction rate because it increases collision frequency and increases the proportion of collisions with sufficient energy to overcome the activation energy. This is another important exam link. Temperature does not just make particles move faster, it changes the energy distribution of particles. More particles have enough energy to react. You can imagine the laboratory warming slightly. In the cooler beaker, particles drift and collide, but many collisions are too gentle. In the warmer beaker, the particles move with more energy. More collisions reach the activation energy. More products form each second. The reaction is faster. This is why food spoils faster when warm, and why many reactions are heated in a laboratory. But in industry, raising temperature can also cost money and may change equilibrium position for reversible reactions. So again, chemists must make careful decisions. Now let's think about surface area. Surface area matters when a solid reactant is involved. A large piece of solid has only its outer surface exposed to other reactant particles. The particles inside the solid are not available for collision until the outer layers have reacted. If the solid is broken into smaller pieces or crushed into a powder, more surface is exposed. More reactant particles are available to collide. So increasing surface area increases reaction rate because there are more exposed particles, leading to more frequent successful collisions per unit time. Imagine a large lump of calcium carbonate sitting quietly in acid. Only the outer surface touches the acid. Bubbles form, but slowly. Now imagine the same mass of calcium carbonate crushed into powder. The powder spreads through the acid. Many more surfaces are exposed. Bubbles form more quickly. The reaction rate increases. This is why small particles can sometimes be reactive or dangerous. Dust explosions, powdered fuels, and fine metal particles can react much more quickly than larger pieces of the same material because the surface area is much greater. The chemical substance may be the same, but the rate can be very different. Now we come to catalysts. A catalyst is a substance that increases the rate of a reaction without being consumed overall. A catalyst provides an alternative reaction pathway with a lower activation energy. Because the activation energy is lower, a greater proportion of particles have enough energy to react. This increases the number of successful collisions per unit time. The catalyst is not used up in the overall reaction, although it may take part in steps along the way. This is a key point. A catalyst does not increase the amount of product that can be formed at equilibrium. It does not change the enthalpy change of the reaction. It does not make the particles magically more energetic. It provides a different pathway, a lower energy path, and because the path is easier, the reaction reaches its products faster. In the quiet laboratory, you might imagine a hill between reactants and products. Without a catalyst, the particles must climb a high hill. Many do not have enough energy. With a catalyst, there is a lower path through the valley. More particles can make the journey. The reaction speeds up. Catalysts are very important in industry because they can allow reactions to occur at lower temperatures or pressures. That can reduce energy use, reduce cost, improve safety, and support more sustainable chemical production. Catalysts are also important in living things. Enzymes are biological catalysts. They help reactions in cells occur fast enough to sustain life without requiring extreme temperatures. Now let's return to the phrase activation energy. Activation energy is the minimum energy required for a reaction to occur. It is the energy needed to start breaking bonds and forming new ones. In a reaction profile diagram, the activation energy is shown as the energy difference between the reactants and the top of the energy barrier. For an exothermic reaction, the products have less energy than the reactants, and energy is released overall. For an endothermic reaction, the products have more energy than the reactants, and energy is absorbed overall. But both exothermic and endothermic reactions usually need activation energy. Even a reaction that releases energy may need an initial push. A spark can start combustion. Heat can begin a reaction. Light can trigger a photochemical change. The activation energy is that first barrier, the quiet gate the particles must pass through. When we talk about changing reaction rate, we are often talking about either increasing collision frequency, increasing the proportion of particles with enough energy, or lowering the activation energy with a catalyst. That is a useful organizing idea. Concentration increases collision frequency. Pressure increases collision frequency for gases. Surface area increases exposed particles and collision frequency. Temperature increases collision frequency and the proportion of particles with sufficient energy. Catalysts lower activation energy and increase the proportion of successful collisions. This is the kind of summary that helps in exam responses. Now let's think about how reaction rate data can be represented. A graph of product formed against time often rises quickly at first, then levels off. The gradient of the graph represents the reaction rate. A steep gradient means a fast reaction. A shallow gradient means a slower reaction. When the graph becomes horizontal, the reaction has stopped producing more product, or the measured change has stopped. A graph of reactant concentration against time usually falls. It may fall quickly at first, then more slowly as reactants are used up. Again, the gradient shows rate. The steeper the fall, the faster the reactant is being consumed. In a VCE chemistry question, you may be asked to compare two curves. One curve may represent a higher temperature, one may represent a higher concentration, one may represent a powdered solid rather than lumps. The faster reaction will usually have a steeper initial gradient. If the same amount of limiting reactant is present, the final amount of product may be the same, even though the faster reaction reaches it sooner. This is important. Changing rate does not always change the final amount of product. It may simply change how quickly the final amount is reached. For example, using a catalyst can make a reaction reach completion faster, but it does not increase the final yield of a reaction that goes to completion. For reversible reactions at equilibrium, a catalyst helps the system reach equilibrium faster, but does not change the equilibrium position. So always ask, is this factor changing the rate, the yield, or both? In reaction rate questions, the explanation should stay focused on successful collisions. Now let's practice the style of an exam explanation. If the question asks why increasing the concentration of hydrochloric acid increases the rate of reaction with magnesium, a strong answer might say this. Increasing the concentration of hydrochloric acid means there are more acid particles in a given volume. This increases the frequency of collisions between acid particles and magnesium particles per unit time. As a result, there are more successful collisions per unit time, so the reaction rate increases. If the question asks why increasing temperature increases rate, the answer needs the energy idea. Increasing temperature gives particles more kinetic energy. The particles move faster, so collisions occur more frequently. Also, a greater proportion of particles have energy equal to or greater than the activation energy. Therefore, more successful collisions occur per unit time, and the reaction rate increases. If the question asks why a catalyst increases rate, the answer must mention the alternative pathway. A catalyst provides an alternative reaction pathway with a lower activation energy. This means a greater proportion of particles have sufficient energy to react. Therefore, the number of successful collisions per unit time increases and the reaction rate increases. Notice that all of these explanations come back to the same calm center: successful collisions per unit time. That phrase is very useful. It helps connect the visible change in the laboratory to the invisible particle model. Now, let's imagine the laboratory again. On one bench, 2 flasks contain the same acid, but one is more concentrated. On another bench, 1 flask is cooler and one is warmer. Nearby, a solid is present as large chips in one dish and as a fine powder in another. A small bottle labeled catalyst rests beside a reaction mixture. Each setup is quiet. Each is controlled. Each changes one variable, and each shows us something about the way particles behave. In experimental design, controlling variables is important. If we are investigating the effect of concentration, then temperature, surface area, volume, and mass of reactants should be kept consistent where possible. If we are investigating temperature, then concentration and amount of reactants should be controlled. If more than one variable changes at once, it becomes difficult to know what caused the change in rate. So, a good reaction rate experiment is not only about timing a reaction. It is about designing a fair comparison. It is about collecting reliable data. It is about choosing appropriate units. It is about repeating trials and identifying uncertainty. And then it is about using collision theory to explain the pattern. This matters because Unit 3 chemistry expects you to move between observation, data, and theory. You might observe bubbles forming faster. You might record a steeper graph. Then you explain it through particle collisions and activation energy. Observation, data, theory. Those 3 ideas work together. Now let's bring the episode gently together. Reaction rate tells us how quickly reactants are used up or products are formed. Collision theory explains that particles must collide with enough energy and correct orientation for a reaction to occur. Activation energy is the minimum energy needed for successful reaction. Concentration, pressure, temperature, surface area, and catalysts can all change reaction rate. They do this by changing collision frequency, the proportion of particles with sufficient energy, the number of exposed particles, or the activation energy pathway. graphs help us see these changes over time. A steep gradient means a faster rate. A horizontal section means no further measured change. A catalyst speeds up the reaction but is not consumed overall. Temperature increases both collision frequency and the proportion of collisions with enough energy. Concentration and pressure bring particles closer together. Surface area exposes more particles, and all of it returns to the same quiet idea. For a reaction to happen faster, there must be more successful collisions per unit time. The laboratory is very still now. The stop clock has stopped. The bubbles have faded. The graphs rest quietly in a notebook. The particles are still too small to see, but the pattern is clearer now. The speed of a chemical reaction is not random. It depends on how particles meet, how often they collide, how much energy they carry, whether they are correctly oriented, and whether a catalyst has opened a lower path. So as you rest now, let the idea become simple. Reaction rates are the visible rhythm of invisible particles. When particles collide successfully more often, the reaction is faster. When successful collisions happen less often, the reaction is slower. And in chemistry, we use collision theory to explain why. This has been Sleepy Steve. Sleep well and let the particles settle quietly in your mind.